Let's take a look at a typical ECG or EKG. And what I have here is just a cartoon that is a generalization of what these look like. And I'll make this point again in a bit, but each of these ECGs look different depending upon what lead you're looking at. And we're going to get into this later, but a typical ECG has 12 different leads, and leads are just different ways of looking at the same event. Again, that'll make much more sense when I walk you through an ECG. But for right now, this is just kind of your stereotypical simplified ECG through a heartbeat. One of the things that you'll note when you're looking at ECGs is that it's going to be on a graph paper, and of course you have an x-axis and a y-axis forming little blocks. And so the x-axis, one block equals 4/100ths of a second. And so again, that's along your x-axis, and that is a number that I want you to know. And then in the y-axis, one block equals about 1/10 of a millivolt. And again, that is a number I want you to know. So I want you to have a sense of scale when you're looking at an ECG paper and you're looking at the little boxes, what the unit is in terms of your x-axis, which is time, and then the y-axis, which is potential change. Now, having said that, looking at this ECG here, I'm just going to point out real quickly, you have a QRS complex, and that's that big spike. This spike here is not an action potential. So you'll recall when we looked at action potentials, you had an out and an in terms of cell membrane, and then you have some kind of metering device, and then you are measuring the potential across the membrane, out versus in or in versus out, and that gets you your potential. This ECG is not that, okay? So you'll recall that with an action potential of a skeletal muscle, the action potential would look like this. It'd go up, and then it'd come down, and then have something like that, where that would be near the Nernst value for sodium, so this is in the area of 60 millivolts. And then it would cause you a little hyperpolarization and then resolve itself. And of course, it happens very quickly. So on first blush, you look at that and say, well, that looks a lot like the R wave. And again, no, they don't. This will help you get a sense of scale. So let's have a baseline here. Okay, so make that the baseline. So the distance from here to here is about 1 millivolt. And of course, you have the same thing down here. Again, 1 millivolt. So the deflection, you have a sense of scale, whereas from here to here is 60 millivolts. So if you were to compare this to this side by side, and you put it in scale, then, of course, the peak R wave here would be 1/60th of that 60 millivolt swing. But you are not measuring an action potential when you're looking at that. You're looking at something else, and again, I will get into that later in terms of walking you through why the pen on the paper moves up and why the pen on the paper moves down when you're doing an ECG. So that's coming, so I'm just going to have to ask you to be patient on that. But my big point is, this is not an action potential. What you're looking at here is going to be the change in the electrical field of your body fluids in response to a depolarizing event of the heart. And I'm going to, again, I have a whole nother lecture on this, and the lecture is called Heart as a Battery. So the heart really is a battery-like thing that has an electrical field around it, and that electrical field, because we are basically salt water, and salt water conveys or communicates electrical fields fairly efficiently, then if I have an electrical field in my heart and I'm a bag of salt water, then that electrical field easily goes through my fluids and creates various potentials in my body. And so when the heart is beating, which you know as a depolarization-repolarization event, then it is changing the electrical field in my body. And so what an ECG is, it is monitoring, or it is reading that change in the electrical field as the heart goes through its cycle. So let's go through and look at some of these labels here. Again, this is time in this direction here. And so we're moving in that direction. So the first thing we have here is a P wave. The P wave is going to be the change in the electrical field in the body as the atria depolarize. So the P wave represents the depolarization of the atria. Then as time goes on, okay, again, this is time moving in this direction, then what's up next is going to be a deflection downward, and we're calling that the Q wave. Then you have a deflection upwards, we call that the R wave, and then a deflection down again below baseline, and we call that an S wave. So this area here we simply refer to as a QRS complex. The QRS complex is what happens in the change of the electrical field in my body in response to the depolarization of the ventricles. Now, the QRS complex is going to be mostly reflecting the activity of the left ventricle as opposed to the right ventricle. That's a function of simple mass. The left ventricle is about 3 times the mass of the right ventricle. So the left ventricle dominates simply because there's so much of it. So the QRS complex is going to be following the P wave. After that, then we're going to have a T wave. And the T wave here denotes the repolarization of the ventricles. And technically, you'll note here the T wave, the slope here is a little less and the slope here is a little more, and that's typical. So a normal T wave doesn't have a symmetry of the rise and the fall. It's skewed to the right just a little bit. Now let me put in some other terminology for you. We have what is called a segment. And a segment is always a straight line. So what we have here then, we have an ST segment. And so the ST segment here is the end of the S wave and the beginning of the T wave. And again, it is a straight line. So if we're referring to a segment, we're referring to a part of this process here in terms of the cycling of the heart. There is no waveform in a segment. In distinction of that, we have an interval. An interval will always include at least one waveform. So we have in this case here, a QT interval right there. And it's from here to here, so the letters kind of tell you what's going on. Goes from the Q, beginning of the Q to the end of the T. And again, it is an interval because it has at least one waveform. We also have a PR or a PQ interval. And in this case here, they label it PR, even though there's a Q there. It is, a lot of times you'll also see this as a PQ interval as well. So you kind of see it both ways. But basically what this is, the PQ interval or the PR interval, again, we're calling it an interval because it has at least one wave, the P wave. That is going to be from the time the atria contracts until the ventricles depolarize and contract. So the P wave is the depolarization of the atria. So it will happen, then you have a little bit of a delay, and then you're going to have the ventricles contract. So, or in terms of an action, in terms of a depolarization event. So the PR or the PQ interval starts at the beginning of the depolarization of the P wave and lasts until the beginning of the depolarization of the ventricles themselves. We also refer to the QRS as typically a complex. There's another wave that sometimes is present, but I don't have it on here, so I'm just going to draw it on here. And it's going to be something like that. Choot, choot. And that is referred to as a U wave. Most of the time it's not there, but sometimes it can be there. So the U wave is thought to be the repolarization of some Purkinje fibers. Someone having a U wave could be perfectly normal. Maybe they've always had a U wave. Sometimes you'll see a situation where someone, if you know their history, will not have a U wave, then all of a sudden they do have a U wave. It may or may not be a point of concern, but we will say that the U wave could indicate a pathology. It may or may not be anything. But if you had a patient and they've never had a U wave, then all of a sudden they have a U wave, it's a sign that says you might want to look further to see what's going on with this individual. Now let me return to the P wave for a second. And again, P wave being the depolarization of the atria. P waves, typically what you have, I just kind of draw it out cartoon-wise there and there and there. And so since it's the depolarization of the atria, it's actually two parts. So the first part here, that is going to be the depolarization of the right atrium. And then the last part here is going to be the depolarization of the left atrium. So you could have a situation where if there is a delay between the right atrium and the left atrium, and remember we have a node that crosses over from the right atrium to the left atrium, if that is delayed, you could see a P wave that looks something like that. A little dip and then something like that. Well, if you have a little dip there, that means there's just simply a little bit of a delay between the depolarization of the right atrium relative to the depolarization of the left atrium. You can also see various forms of the P wave, particularly if there is a pathology. You could see it where, I'm going to draw it down here, you can see instead of being that, it could be this. Okay, you go up, loop, and do that. That could be a P wave, or you could have an inverted P wave, something like that. Now again, these are going to be indicating that there's something different about what's going on in the atria as they depolarize. And again, this will make more sense a bit later. But again, if you have an abnormal waveform of a P wave, then again, it's an occasion to take a look and see what's going on. The normal time between a QRS complex is about 0.83 seconds, and that works out to be about 72 beats per minute, which is in the range of a normal sinus rhythm. Let me say a couple of things about the T wave again. So your T wave, which typically we're saying is that one there, they don't look that way in every lead. Remember, we got 12 standard leads, 12 different perspectives of what's going on in the heart. So when it comes to a T wave, if you're looking at the AVR lead, and again, this will make more sense when I walk you through all the various leads names, so just bear with me on this. And you might want to, when we get to that, come back and look at this lecture so that you now want to know what an AVR lead is. But typically, the T wave in an AVR will be inverted. Which means it's going down as opposed to up. So that would be normal. It could be inverted in leads AVL, lead 3, and lead V1. Again, this will make more sense later. So the T wave, what it looks like is really going to be dependent upon what lead you're looking at. The T wave is largest in leads V2 or V3. Speaking of largest wave, going back to your P wave, the P wave is largest typically in lead 2. Another marker that I want you to know, again, this will become relevant later, is right there at the end of the QRS complex, at the front end of the ST segment. We're going to be referring to this as a J point. Again, I will elaborate a lot more on a J point in a coming lecture. Let me tighten up the definition of some things here. A Q wave is defined as the first deflection down before the R wave. So it's going to be, by definition, following the P wave. So now I'm returning to baseline here. So I got my baseline there. And so the first wave down after the P wave, but before the R wave, we define as the Q wave. I guess my point also here, just because you have a downward wave doesn't make the Q wave, because we clearly have an S wave is also downward, but it's not a Q. The R wave, okay, that's that guy up here on this lead here. The R wave is the first deflection up following the P wave. Now you may say, why didn't you say following the R wave? Well, because a number of leads, you may or may not have a Q wave. You may have a P wave, returns to baseline, and then just goes up. So the R wave may or may not follow a Q wave. But we can say that the R wave is the first deflection upward following the P wave. Now, it may or may not follow a Q wave. So it just depends. And we're going to find out on the next page that sometimes you'll have a double R wave, and if you do, that second R wave is called R prime. Okay, and again, I'll talk about that on the next page. The S wave is the first downward deflection following an upward deflection. And if the upward deflection is an R wave, then typically we're saying the S wave follows the R wave, but the S wave has to drop below the baseline here for it to be an S wave, because the S wave by definition is a downward reflection below the baseline here. So we're going to get into that again on the next page in terms of how you name things. Another thing that I want to make sure that we understand, and again more on this later, in your typical ECG, in this one you see the R wave is much higher than the S wave. And that is true in some leads. In other leads, the R wave is going to be small, and then the S wave is going to be very large. And that would be typical for some of the other leads. So I don't want you to walk away with the impression that the R wave is always larger than the S wave. It's not. It depends upon what lead I'm in. So there are some leads where normally the R wave is bigger than the S wave. Some leads, the S wave is bigger than the R waves. But if you have a lead that normally the R wave is larger, but now the R wave is smaller and the S is larger in a lead where that normally is the case, that's going to typically indicate some sort of pathology. Again, we're going to get into that a lot later on. So the last point looking at this is that there is called a TP wave. A TP wave, if present, or if you can see it, is the repolarization of the atria. Now, you look at this wave here, or look at this ECG here, you don't see the TP wave. The reason you don't see a TP wave, because when is the atria repolarizing? It is repolarizing during ventricular depolarization. So the QRS complex covers up the TP wave. So you normally don't see it. Now there are pathologies such that the QRS complex is not happening during a repolarization of the atria. And if the QRS complex timing is such that it doesn't mask when the repolarization of the atria occurs, then you can see a TP wave. So the ventricles depolarize, QRS, they repolarize, T wave. The atria depolarizes, P wave. The atria repolarizes, but typically it happens when you have the depolarization of the ventricles. All right, so hoping we're having some basic vocabulary here. I don't want you to memorize these numbers here. Don't worry about those numbers. Again, it's just giving you a sense of how long they last. Of course, you can figure that out if you understand the time that 1 square is 4/100 of a second. So definitely know these numbers, but I'm not worried about you knowing these numbers here. So let's now move to some nomenclature. So this first one here is the one we just had. So you have your baseline, you have your Q, you have your R, and you have your S. Next one over, here we have no Q wave, so there's no Q here. We have our deflection, and we're just kind of assuming there's a P wave over here, okay? We're just going to assume there's a P wave. Okay, so the first deflection upward following the P wave is going to be the R wave. And then if you have a second R wave, then we're going to call that an R prime. Now this one gets a little weird in the sense that in literature that is called a RS R prime wave. Technically, it shouldn't be called that because technically that's not an S wave. Okay, that's not an S wave. For an S wave to be an S wave, it's supposed to drop below the baseline. So technically it's not really an S wave, but people have gotten used to calling this particular waveform an RSR prime, so technically it's incorrect, but it's been accepted. So if you hear an RSR prime wave, that's what they mean. Over here, you have an RS wave. So there's no Q involved here, and this is very typical. Okay? In fact, if there is an R wave present, if there is a Q wave present, it's very small. If you have a large, robust Q wave, that typically means there's a pathology, and again, I'm going to talk about that later as to why that is typically a pathology. But if there's a Q wave present, it's usually pretty small. Over here, we have a Q, and we have an R. But again, it doesn't deflect down below the baseline, so you would simply refer to this as a QR wave. And the one down here, we have one sole deflection downward, and they just simply call this a QS wave. So when you hear the word QS, it just simply means one single deflection downward. Seems like to me you just call it a Q wave or an S wave or something, but that isn't what nobody asked me what to call it. So in the literature, you just refer to it as a QS wave, one tick down. And then lastly, one tick up is just simply an R wave. So again, you're going to hear these in literature or read these in literature, so now you have a better sense of what they're talking about. So let's go back and take a look at the action potential of the ventricle. Now this is an action potential of the left ventricle. And again, it's going to, in this one here, they've got it going up to about plus 20 millivolts. And what I've did is I've kind of matched the ECG reading in terms of time sequence with what you would have as an action potential, the depolarization of the ventricle itself. So again, reminding you of scale, this is basically 1 millivolt. Okay, so these two are not scaled together in terms of the y-axis, but I did have them scaled together in terms of the x-axis, so I wanted to match the timing up. Of course, time is moving in this direction here. So what you see here is this is the QRS complex here. Again, it is in line with the beginning of the depolarization of the ventricles. But note that the QRS complex is well over before the action potential is over for the ventricles themselves. So most of the time of the action potential, you're in basically an ST segment. And then what we have as the tissue is repolarizing, so we're heading down towards the end of the repolarization, so somewhere along in here is going to be your T wave. So your ventricles are going to begin repolarizing as this thing here goes down. And of course you return to baseline here, and then you do it all over again. Again, the time here is about 300 milliseconds from here to here. Okay, so again, wanted to give you a sense of what's going on. Again, the time is to scale, but the y-axis is not. Okay, this is 20 millivolts, and this is 1 millivolt there. But again, I just wanted to see so you could understand what's happening in relation to what else is happening. Now, another thing that I want to point out here with this cartoon we have up here, and that is, you will recall that when we looked at action potentials for skeletal muscle or for neurons, we had a refractory period. And again, this goes back to when the voltage-sensitive sodium channels, remember it's a two-gated channel, H gate, M gate. And so when you have that initial depolarization, it deactivates. And that voltage-sensitive sodium channel is not open for business until the membrane is repolarized. So if you try to open it back up before the repolarization has occurred so that it can reconfigure its gates for another round, it's not going to open up. So you have a refractory period in the action potential of a neuron or skeletal muscle. And you'll also recall that you have an absolute refractory period and then you have a relative refractory period, which is at the end of the action potential of the neuron or skeletal muscle fiber. And that we define as you could have another action potential, but you're going to need a bigger stimulus for it. Okay, so I want to do the same thing with the action potential of a cardiomyocyte. And as I said before, it looks very different because it takes a much longer time. An action potential of a skeletal muscle fiber or a neuron is about 2 milliseconds, whereas the action potential of cardiomyocyte is 300 milliseconds. Remember, you got that plateau area up here. Again, if it's plateauing, that means I'm having movement of charge, but I'm having a no net change of charge. I maybe have calcium coming in, but I've got potassium leaving, and so it's even during that plateau phase. And it's only when the L channels, calcium, begin to close, and then I'm having more potassium leaving the cell than I am calcium coming into the cell in terms of number of charge, that the membrane goes down. Okay, so this first light green here, from here to here, that is the absolute refractory period. The tissue is completely unexcitable. Nothing you're going to do that's going to bring an action potential about. Then you have another, and you see this all the time in literature, called the effective refractory period, or the EPR. And so the effective refractory period is going to be here, and then just a little bit of that darker green there. So that is going to be, again, the absolute refractory period plus a little short segment during your phase 3 here, in which a stimulus may cause a cell to depolarize minimally, but will not result in the propagation of an action potential. In other words, a neighboring cell will not depolarize. So what we're talking about here is going to be just this little area here. So I just want to make sure that we're clear. The effective refractory period is simply a period of the depolarization phase of the cardiomyocyte where even if you could kick off another depolarizing event in this darker green, it won't be enough to where you can start the chain of events going from cardiomyocyte to cardiomyocyte. So the effective refractory period simply means that you can't get the reaction going from cardiomyocyte to cardiomyocyte. So the effective refractory period has two parts: the absolute refractory period and then a little bit after that. But during any of this, it doesn't matter what I do, there's no way I'm going to start a chain reaction of one cardiomyocyte causing the next door cardiomyocyte to depolarize. Now, you can't even have an action potential during the absolute, but if you could have a little action potential in that last tail end, but it's not going to lead to another action potential in the next adjacent cardiomyocyte. So we just simply call that the effective refractory period, which means regardless of what happens to the cell, it's not going to kick off a chain reaction causing the next cardiomyocyte to have an action potential, and so forth, so on. After that, then you have the relative refractory period. The relative refractory period is just going to be this area here, and this is where it overlaps actually. So from here to here. So I'm still including that little green there. And then I have the yellow here. And this is where you can have a action potential, okay? But it's going to take more stimulus to cause that action potential to occur. Now again, you have the little double color here because I said in that little green there, I can have an action potential, but it's not going to talk to the next cell. Whereas the yellow here, I can have an action potential, but now I'm getting into the phase where I could have the domino effect of one cardiomyocyte tripping off another cardiomyocyte and having a chain reaction of action potential wave going through all of the tissue. So just make sure you have clear in your mind that little strip of green. You have to think about it a little bit, but that's what that is. So relative refractory period greater than normal stimulus will depolarize the cell and cause an action potential. Will that action potential cause an action potential in the next cardiomyocyte? Depends. If we're in the yellow, yes. If we're in the little green strip, no. And then finally, we have a supranormal period, SNP, and that's going to be this area here. And this is a hyperexcitable period which a weaker than normal stimulus will depolarize the cells and could cause an action potential and also a chain reaction with the next adjacent as well. The cells in this phase are particularly susceptible to arrhythmias because, again, so you can get a problem going on if you have an action potential during that supranormal period, susceptible to arrhythmias when exposed to an inappropriate timed stimulus, which is why when you are doing a synchronized electrical stimulus to bring a heart back to normal sinus rhythm, when you cardiovert, you're going to have to be very careful in terms of the timing. Because if you try to give an inappropriate signal during this little pink phase right there, the supernormal, you can actually kick them into ventricular fibrillation. Now, I probably tossed a bunch of words at you in that last bit there. I am going to go back and we're going to talk about cardioversion and defibrillation. I have a whole block on that, so just hang tight. That is going to become more clear to you in a future lecture. The reason that you have a supernormal period is because by the time you get into the pink here, the voltage-sensitive sodium channels are all set to go again. They're ready for the next round, except you're in this area here where you have not returned to baseline yet, so therefore you are closer to the threshold of these now ready-to-go voltage-sensitive sodium channels that they're easier to depolarize. Again, because this line is above baseline, they're all ready to go, and so it takes less input to cause that reaction. So you're going to hear these terms often in cardiology, particularly the EPR. You'll see that all the time. So again, basically what it is even if you did have an action potential, it's not going to go anywhere in terms of the next adjacent cells. Okay, the last thing that I want to show you in this is going to be kind of lining up to give you a better understanding of how things are when you're comparing the action potential and contraction of a skeletal muscle and the action potential in the contraction of a cardiomyocyte. So you'll recall you have an action potential here. It goes up, it comes down, and then you have your contraction of the, or twitch of the muscle fiber. So this is tension on this one. So you have your action potential, the depolarization, and then follows the twitch. So again, understand the timing. This is going to be 1 to 2 milliseconds, where your twitch could be, 50, 60 milliseconds. So you have that. And again, if you want a more forceful twitch, a stronger contraction, then you can do temporal summations and pop, 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 and then this is just going to go higher and higher and higher. So we've talked all about that. Now let's take a look at the cardiomyocyte in terms of contraction and action potential. And I talked about this a little bit earlier when we were talking about the action potential of a cardiomyocyte. You notice you have your plateau phase there, but look at this. So you have your action potential here. Note that the contraction of the cardiomyocyte is a bit delayed, okay? So it's covering here. So the contraction is a much longer time than the twitch of a skeletal muscle fiber. So it's spread out over a longer period of time, and you're going to note that as this is plateauing, this is the main part where I'm actually having the contraction itself. So the action potential doesn't end until here, and so that's about where my contraction is almost done. And you'll recall that this is advantageous for this tissue to have this long plateau here, because I would not want to have a quick action potential and then have this long contraction, and now these guys are ready to go again. So if I start popping with more action potentials and I'm in the middle of the contraction, no good comes from that. Okay, that's not a good design for the system. You're going to kick in arrhythmias, etc. So that's not how you'd want to design this system. So what you want is you're going to want I want a nice long plateau, so that I want this to be in a plateau phase during the contraction, because I don't want any other electrical activity happening to disrupt the timing of this. So it's very important that the contraction timing is going to mirror the timing of the action potential of the cardiomyocytes. Okay, so hopefully that is helpful. We'll pick up next time.